Well, good morning. This is, already lost the date, March 1st, 9:30 something in the morning. Time for Calculus 1, and I'm sitting in the classroom by myself. It's awfully lonely in here. Wishing some students were here. Do want to go over a couple of minor changes to my office hours for the rest of this week. And I can't remember what I told you on Monday, if I told you anything about these, but in case I told you one piece of thing, I've changed it. Earlier in the week, I thought I was going to need to leave today to run some paperwork over to the Birmingham campus at 3:15. Get it to all the people to sign it in offices that need it before 5 o'clock. So I thought I was going to have to leave as, normally my office hours on Mondays and Wednesdays here are 3:15 to 5:15. And that would have been the case today. It is the case today, but I thought I was going to have to run the stuff over to the Birmingham campus, which means after I got all that paperwork done, the rest of my office hours would be over there. Okay. But because my physical science class, we had finished all the chapters and labs except for one lab, and we can't do that until tomorrow. We didn't need the lab period, so I had some free time yesterday afternoon to go run the paperwork then, so I don't have to do it today. So bottom line there is, where I thought I wouldn't be in the office today, 3:15 to 5:15, I will be. I thought I'd have to go over there and waste time driving, running paperwork, and then spend the rest of my office hours over on that campus. Don't have to now. I'll be here. I already have at least one student who wants to come by this afternoon, so that works out better for him too. But if you need to see me, I'll be in the office. Whether I'm with someone or not, I'll be there from 3:15 to 5:15. Now, unless, of course, we go to a classroom to do tutoring. That sometimes is easier to do than my office. But look for me down there. I'll be glad to deal with it. Okay. Number 2, normally my office hours on Tuesdays and Thursdays are 10:45 until 12:30. Tomorrow that is changed, not permanently, but changed for tomorrow, because as soon as I get out of my 10:45 class and get my stuff exchanged, I need to run to the Birmingham campus to pick up a vehicle because I'm taking my afternoon class on a field trip. That's the lab I was talking about that we couldn't schedule for Tuesday, so we had to schedule it tomorrow. Okay? So that means I will not be in the office, or if I'm in the office at all at 10:45, it won't be for long, because I'll be leaving to go to the Birmingham campus to pick up the vehicle and bring it back to this campus. I hope to be back in the office before 12, mostly because I want to eat a little bit of lunch before we go, but plan to be in the office hopefully as early as 11:45, but if not, hopefully by 12. Okay, but then at 12:30, I have class starting as normal, and then I'll proceed. We're going on a field trip, and once we get back from the field trip, we'll have our final exam, and once that's over with, then I'll be back in the office. Then I've got to take the vehicle back to the Birmingham campus. If I can get it there before 5, I will. If I can't get it there before 5, I'll probably just stay here on this campus for 5:15 like normal, and then drive the vehicle over there. So anyway, Thursday's office hours are messed up a little bit. At least an hour, and probably a little more than an hour, will be spent getting a vehicle. Okay. Friday, normally my office hours on the Birmingham campus, 7:45 to 1. However, I've got my annual physical tomorrow, Friday, and that's going to be at 8 o'clock, so I have to be at the Kirkland Clinic by 7:45, so I won't be on the Birmingham campus at 7:45. And then I hope the physical won't take more than an hour, and if I'm out by 9, then I hope to be back on the Birmingham campus by 9:45. Can't always guarantee things will go as I hope. There could be other issues coming up, but I hope to be back on the Birmingham campus by 10 anyway, hopefully before that. And then I'll be there from 10 to 1 or 9:45 to 1 or whenever I get back until at least 1 o'clock. Maybe later, but at least till 1. All right, those are the changes to my office hours. Still nobody's in the room, so let's get on with Calculus 1. My memory is we finished 3.2 last time, made the assignments and stuff. Now we're moving to 3.3. In this section, we're going to look at how we take the derivative of the products of two functions, and then secondly, the quotient of two functions. So here's the product rule. If f and g, now this, guess what's given here? F and g both must be differentiable functions. If they're not, you can't take the derivative of the product generally, okay? But if f and g are both differentiable functions, then the product fg is also differentiable. And if it is differentiable, what is this derivative? The product of the derivative of the product of f and g is, now this is not maybe like you would expect, okay? Here's how it goes. The first function times the derivative of the second plus the second derivative times the derivative of the second function times the derivative of the first, okay? Now, does it matter which one you do the derivative first? No. You could have done f prime g plus g prime f. Same thing, multiplication of functions is commutative, addition of functions is commutative. Those are the same results. So it's the first times the derivative of the second plus the second times the derivative of the first, or vice versa. Okay? Now, they say it in words. I think they said the same thing I just did. And it said they'll prove the product rule after presenting 3 examples. So let's do the 3 examples first. Okay, I don't think these are on your slide set at all. So let's do example 1. Find derivative of this function. Let me get my pen activated in the darkest color. I'm going to have to turn on the light. I've been waiting for the students to come in. Nobody's come in. Hey, good deal. So good to see you. I've been talking to myself. I've been doing it for about 5 or 10 minutes now. I was just about to get up and turn on the light because I couldn't read very well from where I was sitting. I think that little light. Now it's going to be much better. All right. We've started section 3.3, and we're on the top of page 136. Just have given you the product rule, and it's taking a while for the projector to come on. It's slowly getting there. If you have the key here, if you have two functions that are both differentiable, then the product of those functions is differentiable, and that derivative is, the derivative of a product is the sum of the first function times the derivative of the second plus the second derivative, second function times the derivative of the first. And you can do it any order you want to. You can say first derivative of the first times the second plus the first function times derivative of the second. Doesn't matter. You can exchange the order of the functions and cause multiplication and addition of functions is commutative. So it doesn't matter what order you do them. Just make sure you do both steps. So here is the product function, h of x. And it's a function, it's a product of x squared times 9x plus 2. And we want to take the derivative of that using the product rule. So we're looking for h prime. Now there's 2 ways we can do this. In a minute we'll come back and do it the second way, which I think in this case is actually easier. But let's use the product rule because that's new to us. Okay, obviously you see that's a product of 2 functions. So what would be the derivative of that product? And by the way, both functions are differentiable. Oh, by the way, while you're thinking on that, I forgot to mark you here. Samaria is here. Okay. Say again? You said 2x? Say again? Okay. Okay. Yeah. It doesn't matter. But you got to do all parts of it. Okay? So either way you do, it's fine. So where would you like to begin? 2x. Okay, you did the derivative of the first one, so you'll multiply that by the second function. 9x plus 2. Plus, okay, x squared times derivative of the second. What's the derivative of the second? 9. Okay, let's clean that up a little bit. This will be 18x squared plus 4x plus 9x squared. And what does that wind up being? (27x squared plus 4x). Perfect. Okay? Now, in this problem, I think easier would have been multiply the two of them out. What would that give you? 9x cubed plus, okay, and then take the derivative of that. And that would be what? 27x squared. Ding, 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 ding. I found that much easier to do it that way. But since we're just learning the product rule, I wanted you to do that one first. Very good. But you see, product rule works. Now, a little bit of a timeout here. Didn't we mention in class earlier about the race and the arguments and the disputes over who invented calculus between Newton and Leibniz? Okay. Remember, the contention was that Newton had actually done the work over many years, but didn't want to publish it until we were sure it was actually true. I mean, he's coming up with a whole new method of doing mathematics from scratch, okay? He didn't have a whole lot to go on, and Newton was such a stickler for detail, he didn't want to make any mistakes. So he was testing everything in gory detail. Leibniz, on the other way, is pictured as being this fresh young upstart who was trying to race out there and get it published first. Now, whether I've characterized them fairly, probably not. Okay. But when Leibniz came out with the product rule to begin with, he got it wrong. He didn't check it thoroughly. He published it, and then someone said, hey, this thing doesn't work. And he went back and found out, no, it didn't. And then he hastily found out what his error was and got it corrected. I don't think Newton would have ever done that because he was such a stickler for making sure everything was right. But then on the other hand, that sort of gives credence to the argument that Leibniz was just trying to publish fast and get his credit for it. So I don't know. Anyway, he got it wrong the first time, so don't feel bad if you ever get it wrong. Just get it corrected. Okay. So that's the product rule, example 1. Let's do example 2. I think what I'll do is erase what we've got here. Any questions on that before we go? Okay. Let's do example 2. Y is equal to 2 plus x to the minus 1 times x to the 3 halves plus 1. Did I write it right? I'm having trouble reading. There it is. My eyes keep drifting down the page and I'm seeing something similar, but it's not quite the same. Now, this one, I think product rule is definitely the way to go. It may still be a pain in the neck, but I think it would have been just as big or bigger pain in the neck to multiply through first. But what does the product rule tell you that y prime is? Okay, you're going to take the derivative of this one. So minus x to the negative 2 times the second one, x cubed to the 3 halves plus 1, plus 2 plus x to the minus 1 times, and what do you say, 3 halves? One-half power. I like it. Okay? Now, there are some things you can do to clean it up, so let's do it. What's minus x to the minus 2 times x to the 3 halves? First, the sign's going to be negative. Your x is going to be x. That's the base. What's going to be your exponent? All right. Minus 2. You keep the base, add the exponents. Negative 2 plus 3 halves. 3 halves is 1 1/2. So negative 2 plus 1 1/2 is negative 1/2. The exponent is negative 1/2. Okay. If that's not easy for you to see, put the minus 2 in terms of halves. It would be minus 4 halves plus 3 halves is negative 1/2. Right? Okay. So that's the first part. The next part is that's these two. Now we do those two. That would be negative x to the minus 2 plus, let's do those two first. What would that give you? That would just be 3, wouldn't it? 2 times 3 halves would be 3. 2 over 1 times 3 over 2, right? Okay. X to the 1/2 plus, now we'll do these two. And what does that give you? Three halves x to the again, you got the coefficient, keep the base, add the exponents. Negative 1/2, right? Because negative 1 is negative 2 halves plus 1/2 is negative 1/2, right? Okay. Now, those parentheses are really doing you absolutely no good at all, so I'm going to get rid of them, okay? They just were there to help you see what terms you were grouping together. But now let's combine like terms. Do we have any like terms? Say again? Yeah, here we have x to the minus 1/2. There we have x to the minus 1/2. This is minus 1. That's positive 1 1/2. So that would be 1/2 x to the minus 1/2 minus x to the minus 2 plus 3 x to the positive 1/2. Okay? Now, there's nothing magical about that way of describing it. You reduce 4 terms to 3. You can't really do a lot else. But if you wanted to, you could factor out maybe an x to the minus 1/2. I don't think that would really make it any clearer, but you could if you wanted to, but that would still make it pretty messy. So I think that's as good an answer as any. Let's see what the book got. The book got 1/2 x to the minus 1/2 minus x to the minus 2 plus 3x to the 1/2. Got it. Okay. Now, the question you may be asking yourself, which would be a legitimate question, This was a little involved in taking the derivative, but you did it well. What you could have done was multiply those two binomials to begin with. That would have been really a big pain in the neck. But it's doable, okay? And then you take the derivative of the product and see what you get. You would have gotten the same thing. You want to multiply those out just for the exercise of doing it and see if it's the same answer? It's up to you. Okay, let's try it. Okay, we're going to FOIL this baby. First we'll do the first, and that will be 2x to the 3 halves. That was the easy one, okay? Then you want to do the outers. That's not bad, is it? Plus 2. Well, this isn't going too bad. Let's do the innards now. Okay, that is where it gets to be a little bit of a pain. What do you get when you multiply those two together? +1/2, +1/2. Because -1 plus 1.5, that would be +1/2, right? Okay, and then finally the outer, and that's not too bad. That's plus x to the -1. So maybe this will be the easiest way to go. Okay? All right, let's take a derivative of that thing then. This thing primed would be the first one. Three x to the, goodness gracious, where did it go? There it goes. X to the 1/2, okay, plus 1/2 x to the -1/2. Okay, and then finally, minus x to the -2. Let's see how we did. These two are the same. Those two are the same. These two are the same. Absolutely, you got it. Again, in this case, I think it would have been easier to multiply first and then take a derivative. But they both work. Whichever you see best, you understand best, you follow the best, go for it. Okay? Or if you're lazy, it's easiest. Okay, whatever. Sometimes it's hard to tell. They do have these little notes on the side. One says, note how the prime notation is used in example 2. Fine. I mean, just get used to doing it either way, divided x or y prime or whatever you want to call it. All right, there is example 3. Okay, let's do example 3. All right, example 3. Calculate d by dt of t squared e to the t. And guess what here, team? I can't think of any way of multiplying that. That's as multiplied as they can get. So in this case, product rule is the way to go, just about the only way to go. Okay? What would you get the answer to be? 2t times e to the t plus t squared times e to the t. Boy, not too bad, huh? Now, on this one, you might actually want to factor out something. Let's factor out a t e to the t, and what you have left is 2 plus t. It's no better than the other form. It's just another way of writing it. Okay? let's see what they did. They did it yet another way. They just factored out the e to the t, and that left them with 2t plus t squared. Now, my point here of saying all these different ways you could do that, and why the book chose this way, I don't know. 2t plus t squared times e to the t. Okay? Now, certainly it would have been just as good to put e to the t in front and 2t plus t squared behind. Or written the middle one with 2 plus t in front and e to the t behind. All these are perfectly correct answers, right? If we were doing some of that computerized homework package, like what you call it, WebAssign and stuff like this, guess what they look for? One and only one answer. So, especially when you get here to calculus, and you can write the answers in so many perfectly good equivalent ways, I see no advantage. In fact, I see very little advantage of this over that, just a little bit of advantage of that over that. There is none. All those are correct answers, and yet if you were using those packages, it would have given you 2 out of those 3 wrong, and they wouldn't be. They'd be perfectly correct. So that's one reason I really don't like using those packages, because how they, quote, simplified could vary. Just whatever the mood of the operator is that day. I mean, there's no reason for one over the other. Now, there is what they call a proof of the product rule here. And I don't know, you're not a math major, so it's a pretty nice little proof. It has a good little figure that goes with it that may be helpful to you, but it just takes more time, and I really feel like we need to move on. If you're a math major, please read the proof, go through it, think through it yourself. If you can't follow all the pieces of it, ask me and we'll go over it. Okay? The next couple of slides, they're going to have some pieces of that there, but without the other pieces, it almost doesn't make a lot of sense. So since they are going to show those, I'll get you started on that. Okay? What we're trying to do is prove the product rule here, which is, this is what we're trying to do right here. And according to what the rules say, back to the basics here, the primary definition of that would be FG prime would be the limit, and they use H, I think, don't they? Yeah. As H approaches 0 of F of X plus H times G of X plus H minus F of X G of X over H. Okay? That's how they begin. All right. Now, that's the rule for what the derivative. That's what this thing is, by definition. All right. Before we do anything else, what they're going to do, I'm going to leave off the limit notation for a while just because I don't want to write it every time. But what we're going to do is break this into some pieces. F of X plus H, G of X plus H, I think do the minus first, don't we? It really doesn't matter, I don't think. Yeah, I think it would do the minus first. So let me it just feels right to do the minus first. Okay. Now this just seems pretty arbitrary and capricious, but let's do it. Minus f of boy, they're skipping some steps here, but I'll try to write them all in. F of x plus h g of x plus f of x plus h g of x minus, only I'm going to do plus f of x g of x plus h minus f of x g of x plus h minus f of x g of x. Now that seems like a really dumb thing to do, and all this is over h. Okay. You might say, what are you thinking here? What I did, I added and subtracted the same term to both in here. That adds a 0. Added and subtracted the same term here. That adds a 0. So we really are left with what we had in the other, right? Okay. What we're going to do now is factor out the f of x plus h in the first two terms. So I'm going to come up here and do that. F of x plus h times g of x plus h minus g of x, right? That's taking these two terms and factoring out the f of x plus h, okay? Now, I also want to take the last two terms, this term and that term, sorry, I got them wrong, okay, and do plus f of x, because it's a factor in both of these, times g of x plus h minus g of x, right? That's from these two terms. Now we've still got two terms we haven't combined, and they don't really combine too well, okay? So I'm just going to write them down, plus f of x plus h, g of x minus f of x, g of x plus h. All right. Now, in these two, you got those two are the same. So you could factor those out. And g of x plus h minus g of x times f of x plus h I botched it. Okay, I know it's getting awfully crowded. Let's just go to the next slide. And I think you see, by doing something like this, I think I just combined the wrong terms together. Okay. Basically, here's what you've got. And this is, I don't find this really all that instructive, but it is sort of neat, okay? If you do here is your f of x by g of x, okay? F of x by g of x. When you extend the x to x plus h, that extends the f of x plus h out to here. When you extend the x to x plus h here, your g of x goes to here. Now, if you take a look at this, okay, and this is where I paired them poorly, okay. And I should have gotten those better. I should have been looking ahead a little bit more. But by pairing the ones like we did before, and taking the two terms that had f of x plus h, factoring those out and have the difference here, and then the two terms with g of x in them, factoring that out and having the same, this is f of g plus h minus g of x. This is f of g plus h minus f of x. F of x plus h minus f of x. That would be the portions on the end. In other words, this thing times the difference between g of x, g of x plus h and g of x would be here, and this thing here would be the f of x plus h, the g of x, which would be this distance minus times the difference between this and that, which is f of x plus h minus f of x. Okay? All right, fine. Pretty picture. Yeah, I see what you're saying. So what? Okay, almost. Until you look at the next slide, okay? And that is taking what we just were saying. I admit I combined the wrong two terms. Okay. So this f prime, which is the limit of exactly what we had before, except this time we're going to factor out f of x plus h here and leave you this, plus the g of x times the difference here, okay? And we could go back and show that these all fit in the picture there, okay? But this is just simply f of x plus h times g prime. This is g of x times f prime. And the sum of those two, that is your product rule. Okay? So basically that gave it to you. I just combined the wrong two terms, but rather than go back and redo that. And I think this slide shows exactly what I just said, but maybe a little more. Yeah, splitting these up. This is f of x plus h times that limit of this. The limit of a product is the product of the limits, okay? So that would be this, and that would be, this is simply g prime, and this is h goes to 0, this is f of x. And you do the same for the other one, and you get it. Now, the next little thing they have here is called a conceptual insight. And this is what I was just talking about. The product rule was first stated by the 29-year-old Leibniz in 1685. The year he developed some of his major ideas on calculus. To document his process of discovery, he recorded his thoughts and struggles, the moments of inspiration, as well as the mistakes, in a manuscript dated November 11th, 1675. Leibniz suggested incorrectly that the derivative of product is the product of the derivatives. Not the case. And 10 days later, he wrote the correct one down. Actually, it says he caught his own error. I thought I read somewhere someone pointed it out to him, but he caught his own error and then had to retract and republish. I don't think Newton would have ever let that happen to himself. Maybe it could have, but I don't know. So anyway, let's move on to the quotient rule. You thought the product rule was a little different. You're going to get to learn to love the product rule, and you'll wonder, goodness gracious, let's avoid this quotient rule whenever we can. All right. If f and g, again, have to be differentiable functions, then the quotient of f and g is differentiable for all x's except any x that makes g equal 0. You have to include that. Even though g is differentiable, it still could be equal to 0. It would still be differentiable. Now you have to eliminate those values of x that would make g equal 0, because then the quotient wouldn't be defined. So here's what the quotient rule is, as long as that g of x is not equal to 0. Now this one, it matters. Remember the product rule? I said it didn't matter which one you started with, which one you multiplied by, as long as you get all the pieces in place. And there were only 2 pieces. Just get them in the right order, or any order, and add them together. Quotient rule, You have to be very careful. It's the function on the bottom times the derivative of the function on top minus the function on top times the derivative of the function on the bottom divided by that function on the bottom squared. Oh man, what a pain in the neck formula. Okay? Surprised you didn't get this one wrong too, because this is so much easier to get wrong. Now, basically how I just told you is kind of how I learned the quotient rule. But one time, when I moved to Birmingham, well, actually everywhere I've ever lived, pretty much I've tutored people everywhere, always. I enjoy tutoring. And we had friends from India, and their oldest son was kind of struggling a little bit with his calculus. He was taking his, doing his undergraduate degree in India, but he came back to the States, his parents were here, and he came back here and was studying for his big, major comprehensive exams, which determine whether he's going to get the degree or not. They have a different system than what we do here. If you don't pass your all the exams at the end, you don't get the degree, no matter how many years you've gone and how many courses you pass. If you don't pass the major exams at the end, you don't get the degree. Okay? So he was sweating bullets. He had already had the math and stuff, but he didn't retain it well. It was things. But I don't know if this is strictly in India, but to me the Indian language is very sing-songy. I don't know if you've ever heard it before. People talking that it has a certain rhythm and beat to it for me. And here's how he did it, and I think I'll always remember. I can't even remember for sure how I used to do it myself. He said, low D high minus high D low over low low. Have you ever heard that before? You have? Okay, so it's not just him. And that's how they go by the quotient rule. Low D high minus high D low over low. So it starts with low and ends with low. So low D high minus high D low over low low. Low squared, if you want to say it that way. And everyone who hasn't heard it before finds that far easier to remember than denominator times derivative of the numerator minus numerator times derivative of the denominator over the denominator squared. That's certainly true, but something just such cleaner about low D high minus high D low over low low. Okay. So there is the quotient rule. Now, they do a proof of this one too. Do I want to do that proof? I would say not. Okay. Though it, in the book, takes up a lot less room than the other one did. Now, they do, on their thing, bottom times top prime minus top times bottom prime over bottom squared. To me, low D high is much easier to remember. All right, so let's move on to example 4 then. Here's the function. F of x is equal to x over 1 plus x squared. Okay? How would you take the derivative of that? F prime of x. You got to go? Oh, you're just standing up. Okay. What's that? Yeah. One plus x squared, that's your low, times 1, yeah, minus high, d low, what's d low? 2x, all over 1 plus x squared squared. That's it. Except we can clean it up a little bit. Didn't you know that was coming? All right. Let's see how we clean it up. Okay? That would be 1 plus x squared minus 2x squared. Would you buy that? Okay, over 1 plus x squared squared. Okay? Well, what would that be? 1 minus x squared over 1 plus x squared squared. Now, frankly, that's about as simple, I think, as we can get it. Okay? Okay. If you're going to square that denominator, how you do that is 1 plus 2x squared plus x to the 4th. Remember, you got that cross term in there. The first squared, the last squared, twice the product of the 2. Right? So you have that term there. You could do that. Instead of writing this like this, you could read it like that. I still don't see there's any way to simplify, so to me, that's just it. Either way is fine. But just be sure, if you're going to multiply that, you multiply it completely correctly. Okay, and that's exactly what they got. All right. Sorry. I don't know if the room's getting cooler or if it's getting cooler outside, but it's both. Okay. Yeah, I feel like that too, but I think it's probably the same as it's been all day. But right now I can feel my head just clogging up, and that's what makes me think that something has changed, because it wasn't this way earlier. Okay, let's do another one. This one, I think I'll clear this. Any questions on that? And like you said, either one of those answers right, as long as you do the squaring right. Okay, so you could exchange that for your denominator. Okay. All right. Whoops. I have this on the place. All right, we'll erase all that ink and go to example 5. Calculate d by dt of e to the t over e to the t plus t. How would you proceed? Okay, low, which is e to the t plus t. And what's the derivative of high? E to the t. Minus high d low, which would be e to the t, times e to the t plus It'd just be plus 1, wouldn't it? Okay. Low be high minus high be low. Be low here is e to the t. Here's the t is just 1. Right. I couldn't hear you. My hearing is so bad. Sorry. Okay, and this is divided by e to the t plus t squared. Okay, now that's certainly an answer. Don't know if this is in simplest form, so let's see what we can do to clean it up a little bit. This will be, when you multiply these two together, you get e to the 2t, and then these two would be plus t e to the t minus e to the 2t, right? Minus e to the t. All that over e to the t plus t squared. All right, now I notice that these two go out. Add to 0. Okay? Now, the other thing I sort of look at, I don't know if it's helpful or not, I'm going to factor out an e to the t, and I'm left with a t minus 1. Okay, and that's going to be times e to the t plus t squared. So yeah. I'm not sure if factoring out e to the t would be helpful. I just did it because I saw I could, but it didn't simplify the problem. So I didn't have to do that. But as far as I can see, that's one of the possible answers. This answer here, when I added out the e to the 2 t's, they disappeared. That answer's fine, or that answer. Let's see what the book gives. I was losing it. They said t plus 1, e to the t. They write the t plus 1 first. I'm not sure why over e to t plus t squared. Yeah, we got the same answer. They wrote it a slightly different form, which would have counted mine wrong, but would I care? Probably. Okay. Especially if I worked real hard and you felt like it was right, and then they tell me it's wrong, and I wanted to slap them, but never mind. Okay. Let's do example 6. Ha! Find the tangent line to the graph of f of x is equal to 3x squared plus x minus 2 over 4x cubed plus 1 at x equal 1. Okay. Boy, right now I'm just trying to hang on until I can breathe again. I don't have to stop and go clear my head. Okay, it's find the tangent line to that graph at x equal 1. Now, remind me what we need to know to find the tangent line. Say again. Okay, we need to know y value at the point, which is f of x. Remember, y is equal to f of x. And we've already got the x value, 1. What else do we need? Yeah, we need a slope. Exactly. And what's your slope? Slope is the derivative at x equal 1. Okay? So a couple things we need. As you said, we need to know the y at 1 and x equal 1, which would be f of 1. So let's plug in and see what we get. It'd just be the sum of your coefficients. 3 plus 1 is 4, minus 2 is 2, over 4 plus 1 is 5. So 2/5. Or 0.4. I don't know, whichever you like better. Doesn't matter to me. So there's your y value at x equals 1. Okay? The other thing we need is your slope, which is your first derivative. So you want the slope at x equals 1, which will be f prime at 1. Right? Well, we first need to do what f prime is. F prime of x, what would that be? Here's where it comes from. Okay, it's low, right? Okay, so that would be 4x cubed plus 1. Derivative of your new high, d high, what would that be? That's your 6x plus 1. I'm sorry, you were already doing that. I'm sorry. Minus high, which is 3x squared, plus x minus 2. I don't have enough room, times d low, which would be 4x cubed, 12x squared. Sorry, we're running out of room. Okay. All that over the low squared. Low. 4x cubed plus 1 squared. All right. But we don't really need to haul that around. We need to evaluate that when x equals 1. So let's do that. Now, do you want to combine like terms first or just plug in the 1? Oh, you want to do that first? Let's do it. Okay, the product of those two is 24 x to the 4th. The product of those two is plus 4x cubed. Product of these two is plus 6x. And the product of those two is plus 1. Minus. Okay, now that, if my memory right, is a 12x squared times 3x squared, which would be 12 times 3 is 36 x to the 4th, right? Okay. Minus, I can't read my writing there. Oh, that's a x and then a minus 2. So with the x, that would be a minus 12x cubed. That's minus x times 12x squared. And then we got a plus 24x squared. That's your numerator divided by 4x cubed plus 1 squared. Oh my goodness gracious, I can't breathe. So let's combine our like terms. And that would be minus 12x to the 4th minus 8x cubed plus 24x squared, I think, I don't see any other x squared terms, plus 6x plus 1 over, we'll leave that alone, 4x cubed plus 1 squared. Ugh. That's about as, sorry. It's about as simple as I think we can make that. So let's plug in our 1. F prime of 1, this is f prime of x. So let's plug in a 1. It'll be a minus 12 minus 8 plus 24 plus 6 plus 1 over 4 plus 1 squared, right? Easy to plug in a 1. Only thing easier is plugging in a 0, okay? That's even easier. Plugging in x equal 1 is pretty easy. All right, so what does that give us? Over here we got a minus 20. Here we have a plus 24, so I'm going to wipe out that. So I think what we got here is 11 in the numerator, and we got a 25 in the denominator. Is that what you get? Okay. So now we have the slope is 11/25. Okay, so now we have our x1, or x value, your y value, and the slope. How does that help us get an equation for the tangent line? Remember, we use the point slope formula. Remember that? Y minus y1 is equal to x, or m times x minus x1. Okay? Let me see if I can clean that up just a little bit. Okay. Goodness gracious. All right. So that's y minus 0.4, that's your y1, equal to 11/25 times x minus 1. That's your x1. Now here we have fractions and decimals all in the same problem. That's a little bit, to me, a pain in the neck. So let's rewrite this as y minus 2/5, right? That's what we had up here anyway, is equal to 11/25 times x minus 1. Okay? And if you multiply that through, that would be 11/25 x minus 11/25. So if we add 2/5 to both sides, and add 2/5 here, but I want to write that in terms of 25ths, so that would be 2 times 5, which would be 10, over 5 times 5, which is 25. Okay? So that leaves me with, I'll write it up here, y is equal to 11/25 x minus 1 over 25. Okay? And if you wanted to write that in decimal form, that would be something like 0.44x minus 0.4. Okay? Let's see what form they... thank you very much. They leave it as y is equal to 11/25 x minus 1/25. I know I wrote all over the page. Did you follow? Okay. You all right with it? Any questions? I can't hear. Yeah, okay. So we got that same answer. All right. The next problem is actually a physical problem, a physics problem, okay, an electrical physics problem, okay? It's asking for the power delivered by a battery. Power that a battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery. And that's what the little r is here. This is your battery. It's giving it a voltage, but also has a little bit of internal resistance. Okay? And then your laptop, that's the capital R resistance, or whatever your resistor is, a light bulb, whatever it is. Okay. For a battery, a voltage V, that's not counting the resistance, internal resistance, and internal resistance R, the total power delivered to an apparatus of resistance, capital R, as shown here, is, and they just give you the formula, without deriving it. Thank you very much. Okay, you can derive it in physics class if you're really interested. It's not that bad to do, but don't have time for it here. Let's just write it. P is equal to V squared R over R plus little r squared. Okay? That's your power delivered by the battery of voltage V, internal resistance little r, external resistance, and it's voltage delivered to an external resistance of capital R. Okay. Now, the question is, how does that power delivered change as you change the resistance? Let's just say that you have a variable resistor here that you're tuning or adjusting. How does the voltage delivered, the power delivered by this battery change as you change the resistors? What's that? What happens to the power delivered by the battery as you change the resistance? Let me see if I can think of some sort of a reasonable application of this. What's that? Yeah, that is the power that the battery is supplying when you have a voltage of the battery, capital V, the internal resistance of the battery, little r, and the outside resistance is R. And say, how does that power vary as you change the outside resistance? So let's say that I could imagine and picture situations in which you have what they call a rheostat at the end, and you're adjusting that. It's kind of like, but it's not the same as tuning your radio receiver when you're wanting to go to a different station. Okay? It's kind of like that. The only thing is then you're varying capacitance is really what you're doing with that, not resistance. But it's something like that. And how does the power change? So what we're looking for is dP/dr. So the A part of this problem is calculate dP/dr. Okay? Now, remember, this is a constant and this is a constant. Okay? How does it change the power delivered when you adjust the resistor on the outside, not changing anything about the battery itself, either its voltage or its internal resistance? Well, this is obviously a quotient rule problem. So what would that be? Okay, you like to start up there. Just because I like to do low D high, I want to write down the low first. R plus little r squared. It doesn't matter. It's just my little thing. Times D high. And you're taking the derivative with respect to R. Just V squared. Because V squared is a constant. R as your variable is to the first power. Derivative of that would be that. Minus high-low, yeah, that's your V squared R times, okay. Now, I don't like one thing about this problem. There's probably several things I shouldn't like. But the one thing I don't like about it, it requires you to use something we haven't done before. but it's basically 2 times this thing. And then times derivative of r, which is 1. So basically, that's your power rule there. 2 times what's on the inside. Okay. And all that is divided by r plus r squared, so that would be to the 4th power. Okay. Now, this is assuming v and r are constants, little r. All right, we got a little bit of stuff we can do to clean up here. That would be r, not for any particular, reason, except I like to do it this way. Remember, your variable is capital R, and the v is a constant. So I like to write constants first. V squared R plus, and then the second, whoops. Oh, what a pain in the neck. I forgot that. Let's go back. We got some more work to do. Sorry about this. Okay. The work we got to do, we got to multiply that out. This is going to be capital R squared plus 2 times little r times capital R plus little r squared. Right? You buy that? Square in the binomial. This thing here. You got to square the first, twice the product of the 2, square the last. If you don't remember that, take them off to the side. Do r plus r times r plus r. R plus r times r is r squared. And the outers are r times little r. The inners are little r times r. So that's 2r little r, r. And then the last are r times r squared. Okay. So if you need to, go over and FOIL that. Okay. This is what's being multiplied by v squared minus, now let's combine all those together. You got one sum still in there. So this is going to be a 2v squared r squared. That's these multiplied together. Plus 2, and only it's going to be a minus, sorry. Because that minus is still in front, minus 2v squared little r capital R. Okay. It's a little messy, but if you would multiply this 2 by there, that'd be 2 capital R times 2 little r, and multiply that by each of this, 2 capital R times VR, v 2, and it's a minus 2. V squared R squared minus 2 V squared little r r. Okay. Sound like the pirate joke. R. Now, that's your numerator, and we're going to leave the denominator pretty much like it is unless we have to. R plus little r to the 4th power. Okay, we still got one more set of parentheses to clear, and this will be r squared v, except I said I wanted to write the constants first, so let me go back and do that. It's just my picky thing here. This would be v squared times r squared plus 2 little r v squared times r plus r squared v squared minus 2v squared r squared minus 2v squared r, okay, divided by r plus r to the 4th. Now let's see if there's any common factors here. Any common anything. Okay, here you have v squared r squared, here you have minus 2r. So that would be a minus v squared r squared. Okay, say that one more time. Okay, this little r squared v squared, that one, I'm combining these two. That would be a minus v squared r squared. Okay, well, let's see if there are any others. This is a 2r v squared capital R, and this is a minus 2. Is that what you were saying? This one and that one, they're exactly the same but opposite signs, aren't they? So they add to 0. That's nice. And then all we have left is plus r squared v squared, which is a constant. And that's divided by r plus little r to the 4th power. Okay, I don't think there's much else we can do to that. So let's see what they've got. Oh my goodness. Okay, what they do here now, they factor out a v squared, and that leaves the numerator. I'm going to reverse the terms to be little r squared minus capital R squared over capital R plus little r to the 4th. Okay? I think that's what it winds up being. Let me see what they got. V squared times, whoa, not quite. Okay? Here's why. This will factor as little r plus capital R times little r minus capital R. We know that, right? Okay. What you may not know, well, no, it's fine. You could write this as, it doesn't matter the order here, r plus little r times, and r plus little r cubed. Well, this one and that one are exactly the same. Doesn't matter the order when you're adding. It does when you're subtracting but not adding. So now we've come up with the answer being, this answer here is v squared times little r minus capital R over capital R plus little r to the 4th. Now this is interesting in that most of the time the internal resistance of the battery is less than the external resistance that you have out there. I mean, internal resistance of the battery is pretty low. Usually your resistors out there are fairly large, okay? So basically this is going to be a negative number, meaning as you increase the resistors here, you decrease your power. Not by a lot, but by a little bit. So that is a decreasing function. Of course that makes sense. As you increase the resistance out there, you're going to decrease the power put out by the battery. So I hope that makes sense. Okay? Now, the B part of this one, it says, where in the graph of P versus R is the tangent line horizontal? So the B part is where the tangent line horizontal. Now, when is the tangent line horizontal? What is the slope of a horizontal line? 0. And if indeed you want the tangent line to be 0, that derivative, which is this thing right here, has to be 0. Well, when is that true? Well, it doesn't matter what you do down here, that's not going to positive, raised to the fourth power is positive. This went there. B won't be 0. Only thing that can be 0 is this. So that's when little r is equal to capital R. And that's indeed what they got. When capital R is equal to the little r. So that's where the slope of the tangent line will be horizontal. All right. Now, the next graph shows that. No, it doesn't. Okay. They did a couple of their steps in here, which, man, we've already done, so we don't have to go back and redo that, or that, or this. But here is the last part. Here's the graph of that power, where power is the output power when your resistance, capital R, is going from 0 to some positive value. Okay? Well, certainly if this capital R is 0, your resistance, your power is going to be 0. Then when you start adding any kind of resistance to that, then your power is increasing big time until it gets to the place where capital R is equal to little r. That's when you have a horizontal resistance. And from there on, it's declining. And what I had said before, most of the time R is always less than your external resistance is just always greater than the little r, and therefore you have a negative slope. Just about always. If you had an outside resistance that was very, very small, less than the resistance of the battery, then you have a very large slope on that power curve. Extraordinarily large. Okay, and that's your graphical insight. There's your summary. You want to do the equations? Let me make sure there's nothing else. No, there's not. Okay, you want to do the preliminary questions? All right. Are the following statements true or false? If false, state the correct version. So here's A. FG denotes a function whose, okay, you don't have a book today, do you? FG denotes the function whose value at x is equal to f of g of x. True or false? No, that's actually false. This thing right here is the composite of f and g, f circle g. Composite of f and g, that's what that is. Okay? The function whose value, the fg, would be the function whose value is f of x times g of x. That's not the same as this. This is f of g of x. So there's two ways you can make that true. One way would be f circle g implies f of g of x. The other way is fg implies f of x times g of x. Okay. Now, I don't know which way they wanted it corrected in the back, but both of those would be corrections to make it true. Let's see if we can find out which one they were looking for. 3.3 preliminary questions. False. The notation fg denotes the function whose value x is f of x times g of x. That's the one they wanted. Okay? Number B. F divided by G denotes the function whose value at x is f of g divided by f of x divided by g of x. True or false? That is true. That one is true. Good, they got it right too. Okay? Number C means yes in Spanish. Okay? The derivative of the product is the product of the derivatives. True or false? No, that's really shorthand. Derivative of a product is the product of the derivatives. Now, sum of, derivative of a sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives, but not true for this. What that's saying was what Leibniz got wrong. He was saying f g prime is equal to f prime g prime. We know that's not true. What is f prime g prime equal to? It's what? Okay, I can hear you say something. I can't make it up. Okay, f of x. No, g prime of x plus f prime of x, g of x. You got it. That is the correct one. Now, the order you do those, it doesn't matter. You could have put the g prime in front, that prime there. You could put g prime here, that prime there. You could put this over here, this over there. I mean, you could rearrange any of those that you wanted to, but you have to have those two pieces to it. Okay? And I'm pretty sure that's how they wanted it done. False. Derivative of a product is, they started with f prime g plus f g prime. Either way you want it. You could have done g f prime. I mean, it doesn't matter. Okay, let's see. I think we got to go clean some space here. And let's do D. D by dx, this is Leibniz notation, of fg evaluated at x equal 4 is equal to f of 4 g prime of 4 minus g of 4 f prime of 4. True or false? Why is it false? It needs to be a plus. It's absolutely correct except for the plus sign. So it is false. You put the plus sign in there, it's true. So that's all you need to do that one. It is false, but put the plus sign there. Got it. Okay? Now E. This was D. Here's E. Pen is all tangled up. Okay, E. D by dx of fg at x equals 0 is equal to f prime of 0 g of 0 plus f of 0 g prime of 0. What you think? True. Absolutely true. All right, let's do number 2. Find f over g prime at 1 if f of 1 is equal to f prime of 1 is equal to g of 1, and they're all equal to, let's see, 2, and g prime of 1 is equal to 4. So find f prime divided by g prime. First, tell me what that is. Say again. G f prime, low d high, minus high d low f g prime over g squared. Right? Low, low. Right? Okay. Now let's plug in the values. G at 1 is 2. F prime at 1 is, no, it's 2. All those are equal, right? Okay. Minus F, which is 2 times G prime, though that's 4, over, which is 4. 2 squared is 4. Got it. So this will be 4 minus 8 over 4, which would be minus 4 over 4, which is minus 1. I hope, because I did it really too fast. Minus 1, that's sure enough gives it to us. One more. I think I'm going to have to clean some screen. All right, number 3. Find G1, G of 1, if f of 1 is equal to 0, f prime of 1 is equal to 2, and f g prime of 1 is equal to 10. How would you do that? How would you proceed? What is fg prime? F, I couldn't hear you. You could do fg prime plus f prime g, right? The derivative of a product is the first times derivative of the second plus the second times derivative of the first, or however you want to say it, right? So now let's plug in when each of those is evaluated at 1. What's f of 1? 0. It doesn't matter what g prime is, so we don't care. We don't know it anyway. G prime, okay, plus, what's your f prime at 1? 2. And what's your g of 1? That's what we're looking for. G of 1. Okay, and this is equal to 10, because f prime of 1 is 10. And that's what that's equal to. Well, this one's 0. So we've got 10 is equal to 2g of 1. What's g of 1? Divide by size by 2, and you get, oops, I did the wrong one, 5. Okay, I put my line through the wrong one. So this will be 5 is equal to g of 1. Let's see. I did it fast, but sure enough, that's what they got. Homework exercises here will then be any of the odds 1 through 5, any of the odds 7 through 11, either 13 or 15 or both, any of the odds 17 to 37. There's a whole lot of those. So do some of each of those. Okay, try several of those. Then do any of the odds 39, either 39 or 41 or both. And then you can do any of the odds 43 through 53. I would do some of each type that is of any interest to you. Any of the odds 43, let me see, did I say it right? Yeah, 43 through 53. No, I'm sorry, through 55. Through 55. Okay. Now, looking at further insights and challenges, I don't see anything there that might lead to a paper topic. But if you see something, go for it. All right. Do we have time to get started in 3.4? What's that? Yeah, so we really don't. So we'll start there next time. 3.4, rates of change, which almost feels like something we've already done before, but we'll do it and do that. It's a little bit longer section, but hopefully we'll get it done rather quickly. Okay. Then you've got higher derivatives. We'll do next. That's going to be fairly short. Trigonometric functions, those are going to take, it's a very short section, but there's a little bit of work to do there. Then we get to the chain rule, which is a great thing. You need to know it. And it's a little bit longer section, so that'll take a little while. And then we do implicit differentiation, which is something we need to know how to do. I hope the section is not too long. It is, sort of. And then derivatives of general exponential logarithmic functions. We really need to do that. Yo, this is one long chapter. And related rates. Boy, I love related rates problems, but I think we're probably going to have to skip those just because we this is such a long chapter. But we'll see. We'll go from there. Good deal. Hopefully we'll move right along. Have a good weekend. Glad you came.